Okay, in this video we're going to look at applying kinetic theory to understand continuum quantities like pressure and temperature. For this example, we're going to consider a box length of L. And this particle is moving with speed c in the positive x direction inside the box. So the particle travels until it hits the wall and then it rebounds and is now travelling in the opposite direction minus x with negative c velocity. To approximate the pressure due to this particle, we're going to consider the force that acts on this vertical wall during the collision. And so to start with, we're going to consider the change of momentum of the particle. So our force is equal to our mass times acceleration, which is equal to the rate of change of our momentum. And so the impulse, or the change of momentum, is equal to the momentum of the particle as it travels towards the wall minus the momentum of the particle once it's rebounded off the wall, as follows. And we're going to consider the time interval delta t, which is the time it takes for the particle to travel twice the box length, so one full distance there and back. So delta t, distance divided by speed, is equal to 2 times L divided by Cx. And so the force in the x direction due to the collision of the particle with the wall is 2mcx divided by delta t, which can be simplified as mcx squared over L. Now this is the force due to a single particle moving in the x direction. If we generalize this to n particles moving in 3 dimensions, we get the following. First, the force for n particles in the x direction, and then in 3D, assuming isotropic motion, we get this expression for the force due to n particles in 3 dimensions, noting that the velocity cx can be converted into a general 3D velocity c by assuming isotropic motion. And so then to find the pressure, which is a force divided by an area, we define the area of the wall as A, and so we get as our pressure nmc squared divided by 3L length times area A. And this can be further simplified by noting that LA is volume V and that mc squared is almost the particle kinetic energy half mv squared. And then finally we can see that the pressure due to the particles colliding with the wall is equal to 2/3 times the particle kinetic energy times the number of particles divided by the volume. And we can now extend this to consider the temperature by making use of the ideal gas equation, which says that pressure times volume is equal to the number of moles times the gas constant times the temperature. And the number of moles m can be defined as the number of particles divided by Avogadro's constant, Na. And we also substitute in the expression defining the pressure that we just defined. And this simplifies to an expression that says that 2/3 of the kinetic energy of the particle is equal to temperature times by the constants, the gas constant R divided by the Avogadro number Na. And this can be further simplified as K, which is the Boltzmann constant. So we can then obtain an expression for temperature due to the particles as 2/3 times the kinetic energy of the particle divided by the constant K.